So in this video, I'll be going through the practice exam. Remember that the exam is covering sections 3.3, 3.4, all of chapter 4, and all of chapter 5. This is a list of topics that we'll be choosing problems from, but these are just the sections in the corresponding chapters, and so this should give you a vague idea of what you should be comfortable completing problems on. So starting with the true-false, this equation has only one solution. Well, if we wanted to solve it, we would add the 34 to the right-hand side. So we'd have x to the fourth equals 34. And if we then take the fourth root of both sides, so doing the fourth root, then on the left we just have x, and on the right we have the fourth root of 34. But because we took an even root, being the fourth root, and 34 is positive, we actually have a plus or minus value as well. So it can be the positive version of this number or the negative version, and so the answer is false because there are two solutions. The half-life is defined as half the initial value. That's just not the definition of it. The half-life is half is the amount of time it takes for the function to half an output value. It's actually completely unrelated to the initial value, so it's false. Suppose the doubling time of a population is 8 days, then after 24, the population is twice as large. So if I know the population, if I know the doubling time is 8 days, I start with some initial amount, A, and I go 8 days into the future, it would have doubled to 2A. So this is after 8 days. And then I go another 8 days into the future, again, and it doubled to 4A. And I go another 8 days, and the 4 would have doubled, so I would have had 8. And now I've proceeded to go 8 plus 8 plus 8, so 24 days. But my population is 8 times as big, not twice, so this is not true. You could, of course, find a formula here, but that would take some time, maybe because it's a true-false question. It should indicate to you that you can do this a little bit faster than if you tried to find the full formula out. The following are examples of power functions, yes or no. We need to convert them into the form where we can recognize them. The first one is fine, it's really right. 1 times x to the first power, so yes, it's a power function. The second one we can write as, again, 1, it's coefficient 1, times x, but the power is 1/2 because the square root corresponds to the 1/2 power as a fractional exponent, so that one works as well. And then for the last one, we can simplify it a little bit. We have an x cubed in the numerator and x to the 7th in the denominator, so we can say this is 1/2 times x to the negative 4. And that's a power function, so that's true. This equation has one real solution. So this is asking you to find the discriminant. I guess it's implicitly asking you to find the discriminant. You could try to solve it, but then if it doesn't have a solution, then you've kind of wasted some time here. So to do the discriminant, you would do b squared minus 4 times a times c, and b squared is, well, b is negative 5, so b squared is negative 5 squared, minus 4 times a, which is 1, times c, which is 87. And so now I'm doing 25 negative 5 squared, minus 4 times 87, and I don't know what 4 times 87 is. It's like 348, right? I think, but it doesn't matter because if I do 25 minus that number, I'm going to get something that's very much negative. And so we can definitely say that it's less than 0. And because it's less than 0, this has no solutions. So this equation has no solutions. If you tried to use the quadratic formula, you would encounter this, right? Because the determinant shows up under the radical in the quadratic formula. That's how we know how many solutions it has. If you tried to find it, you wouldn't be able to compute it, and so it's another way you could show that it has no solutions as well. Okay, an exponential function is decreasing or decaying if its growth factor is negative. That is not true. There's actually a lot of things wrong with this. So first of all, b has to be greater, the growth factor is b, which has to be greater than 0 always. You can never have it be negative, so that should be an indication that this is wrong, but maybe what this is getting at is that if r is negative, which is the growth rate, then it's decaying or decreasing, but it's not the growth factor. That always has to be positive. It can never be negative. Vertex of this function, there's a couple of ways to do this. You could complete the square, but that would be a little bit of work. You could also use negative b over 2a for h, and then k is the function value at h. So h is, well, negative b is negative 8. 2 times a is 2 times 4, so this is negative 1. So at least that matches the horizontal component of the vertex, so potentially this should be it. And if I evaluate the function at negative 1, I would get 4 times 1 is square negative 1, plus 8 times negative 1 plus 1, so this is 4 minus 8 plus 1, which is negative 4, plus 1, which is negative 3. And so then, yes, this is the vertex. Remember, this is the h, comma, k. It's the ordered pair. And you can find the h value using this, and then just plug that into the function, and that will give you back the value for k. Some power functions have horizontal intercepts, others do not. That is true. Something like say x squared has a horizontal intercept. 1 over x doesn't have either horizontal or vertical, so that is true. Okay, this function, what can we say about it? Well, the growth factor b is 1.45, which is greater than 1. That should be clear, right? It's 1.45. So it's greater than 1. So it's not b or d, because those are both saying that it's less than 1, and it's not. So we can immediately rule those out. And we know that r is b minus 1. Which is 1.45 minus 1, which is 0.45, right? Positive growth rate, growth factor greater than 1, those will occur in pairs, and so the answer is A, which is what would have to happen. C is not even possible. You cannot have a growth factor greater than 1 and then also have a negative growth rate, so in any case, you could rule this out pretty quickly. It has to be A. This equation has solutions of what? So in order to solve this equation, we can add, or we can subtract 34 from both sides. So we can say x minus 1 equals 41 minus 34, which is 7. So we have the square root of x minus 1 equals 7. We can then square both sides of this, because if we square it, the square root will cancel out. So we have x minus 1 equals 49. So then x is 50, and that would be that choice. If you said A, you might have thought that this has a negative value as well, but no matter the sign of what the square root is, if we square it as we're doing here, it would become positive. And so square that number is always positive. Squaring 7 is always positive, right? It's just 49. So then the only solution can be 50. What is the vertex of this function? Well, vertex form, remember we have a t minus h squared plus k, and we just equate them here. So h is 5, k is 12, and so that's choice C. This function quadruples every what amount of time? Well, remember that if we have a function that looks like a times some number c to the power t divided by t, then this function scales by the value of c. So if it's 4, it would quadruple every t, capital T units of time. So if c is 4 as it is in this function, and then t is 7, it means that it's quadrupling, multiplying by 4, every 7 time units, and that would be d. You could also test this as well, because f of 0 is 2, and f of, you can start to plug these in and see what you get. And if I plug in 7, then I get 2 times 4, which is 8. And so then this quadrupled, multiplied it by 4, and that happened after 7 time units. So you could guess and check through here, I guess is what I'm saying. Next, write the formula for the function that has this vertex and has coefficient a equals 6. Well, we just did a question like this with vertex form. We want a x minus h squared plus k. A, we're told, is 6. The vertex is -4. So -4, -5. So subtract -4, square it, plus -5. And so this is 6x plus 4 squared minus 5. So that would be the function. There's not really another another way to do this. You could use the fact here that -4 is h, so then that's -b over 2a, and you know a is 6. But this is going to be a little bit of work because you also have to determine what the constant number c is on the end. So this is really the strategy that I recommend that you take. These 4 functions are, so there's 4 exponential functions here. Which one of these are true? So the initial value of f is larger, so the initial value for f is here. The initial value for w is there, and that is bigger. It's further up on the y-axis, it's a bigger value. H has a continuous growth rate smaller than the continuous growth rate of g. Well, h has, it's a decreasing function, so its continuous growth rate, and indeed its normal growth rate, have to be less than 0. But g is increasing, which means that k has to be greater than 0. And so even though we can't compare them any more than this, we can say that this is true because the one for h is negative and the one for k is positive, so it's, of course, it's smaller. Both f and g have a vertical intercept. Well, yeah, we just identified it. It's on the graph. Any exponential function has a vertical intercept always, but never has a horizontal. So that's actually why this is false, because no exponential functions can have a horizontal intercept. Both w and g are exponentially decaying. W is decaying, yes, but g is increasing. We just identified that, and so this is false. The growth factor of f is larger than 1. That is true, because f is increasing, so it would have to have its b value greater than 1, or equivalently, its growth rate would have to be positive, or its continuous growth rate would also have to be positive. The growth factor of g is equal to the growth factor of f. This might take some thought as to why this is either true or false. We know that the initial value, so f and g have the same initial value. right? They have the same vertical intercept. We actually identified that in part C. But they're not the same function, right? They're clearly different functions here, but they have the same initial value. So they cannot have the same growth factor. If they did, because they already have the same initial value, they would be the same function, but they're not. So that's not true. None of the functions have a positive continuous growth rate. Well, we just identified that g and f have k greater than 0, and so that is false as well. So the only true options are a, b, c, and f. Okay, now we need to simplify these expressions so that you only end up with positive exponents. So this may require using fractions. Maybe we'll see why in a sec. So I can start this with, I have a 7th power of x there and a 5th power in the denominator. So I'm dividing that same base, so I can subtract the exponents, times y to the, I have a 1st power in the numerator, 2nd in the denominator, so 1 minus 2. And then for z, I have 10 and a 3, so 10 minus 3. So this is x squared y to the negative 1 z to the 7th, which is true, but I have a negative exponent for y, and so I need to write this as x squared z to the 7th over y. I guess you could leave it as the 1st power, so that this all has positive exponents, and that was why I said this may require you use fractions to convert the negative exponent into a positive exponent. Next step, similar process, negative 4 in the numerator, 1st power of the denominator, so minus 1, times y, 4 minus 5. So here this is x to the negative 5, y to the negative 1. These are both negative, so I need to write it as 1 over x to the 5th times y. And I could leave y as the 1st power, but you don't need to. So remember that if you have, say, like a to the negative p power, this is the same as 1 over a to the p. That's a definition we had in section 5.1, and that's what we're using here to convert it into a positive exponent. Just applying it to both terms. Okay, for each of these power functions, write a formula that could describe them. So you need to have negative values of constants if you determine that they should be negative. For the first one, I know that it has to be a negative power because I have an asymptote at 0 and I have a vertical and horizontal asymptote, so I have to have a negative exponent. And we can identify that it also has to be an even integer because both sides here are above the y-axis, or above the x-axis rather. And so it's a negative even integer exponent, and it's a positive coefficient. So there are many choices that you could make. The simplest would be choosing a positive coefficient to be 1 and choosing a negative even integer to be negative 2. And so we could just say this is something like x to the negative 2, but there's other choices you could make so long as you satisfied these two constraints. For the other one, we see that we have asymptotes, so that suggests that we have a negative power, a negative exponent. It's on both sides of the x-axis, so it has to be an odd, and it's defined on the left side of the, it's defined over here on the left side of the y-axis, so it has to be a negative odd integer and not a fractional power. And the coefficient has to be actually negative. There's a couple of ways to see this. You could test points here and maybe here as well, but only once is necessary to determine if it's positive or negative. Or you could remember that when we defined the function like this, the branches were on this side. And so what's shown is the reflection of it. So I have to have a negative coefficient and a negative odd integer exponent, and so that could be something as simple as negative x and negative 1. But any negative coefficient, I could do negative 2x and negative 1, or even negative 3. Anything like that would be fine. And then for the last one, there's no asymptotes. It's defined on both sides. It looks like a quadratic, essentially what it is, x squared. But in general, this would be an even positive integer exponent, and it's opening upwards, but we can see that the coefficient would be positive. So x squared isn't the only option. I could do 3x squared. I could do 10x to the 12th. You just have to satisfy these two conditions. Okay, next. This is a quadratic function of f. The formula is not known. We just have the graph. And then we have another function g, which is only defined by its formula. What can we say about the two functions? Do they have the same horizontal intercepts? Well, that's not immediately clear, at least for g. We could determine that for f, because the horizontal intercepts are here and here. So f has horizontal intercepts plus or minus 3. And we could write g of x, we can factor it, we can take it out of 2, and we would have x squared minus 1. And then we can factor x squared minus 1 to x plus 1 and x minus 1. And so the horizontal intercepts for g are negative 1 and 1. So g has horizontal intercepts plus or minus 1. So they're not the same. F and g have the same vertical intercept. That you also have to test. So to get the vertical intercept, we would do f of 0, and f of 0 on the graph is negative 2. And g of 0, just putting in the 0 into the function, is also negative 2. And so, yes, they have the same vertical intercept. Do they have the same vertex? We have to be a bit careful about this. So f has a vertex at negative 2, 0, negative 2 is the vertex for f. And then what is the vertex for g? You could complete the square. You could graph it. But what might be easier is if you use h equals negative b over 2a, and from the way that g is defined here, negative b is 0, because this is 2x squared plus 0x, I guess you could write, minus 2. So b is 0, so h is 0. And then k is g of 0, which is negative 2. And that means that the vertex for g is 0, comma, negative 2, which is the same one that we had for f. So that is true. So even though they have different horizontal intercepts, even though we said that these are plus 1, plus or minus 1, plus or minus 3, they still have the same vertex. So you'd have to be a little bit careful about that. F and G have the same axis of symmetry. Well, yes, of course, because they have the same vertex. So their axis of symmetry has to be the same line. Actually, that could be true even if k was different, like the negative 2 and the negative 2. Of course, they are the same number here, but if this was like negative 3, then this answer would still be true. Changing where the vertex lies on this line doesn't change the fact that it still has an axis of symmetry at x equals 0. It's the line here. And do they open up the same way? Well, f of x opens up, just looking at it, it opens up, and g has a positive a coefficient, it's 2, and so they do open the same way. They actually both open up, and they're not the same function. uh, y because they have, for one, they have different horizontal intercepts. So um, they can't be the same function, right? G of x actually looks something like this. So it's approximately G of x. They're not the same function. All right. Determine the vertex of this one. We've done this a few times here. So we could do h equals negative b over 2a. You could complete the square, but that would be a little bit of work. So if you do it this way, then this value, negative b is negative 4. 2 times a is 2 times 5. So I get negative 4 over 10, which is negative 2 over 5. So that would be the value for h, and then I want to get the value for k, which I do by evaluating the function at the h value, at the x coordinate for the vertex. And if I put in negative 2 fifths, I have 5 times negative 2 fifths squared plus 4 times negative 2 over 5 minus 2. You could leave this as a fraction, but as a decimal, but you don't need to. So this is 5. We have to square that first, which is 4 over 25. Minus 8 over 5 minus 2. That's the 5 cancels with 5 in the denominator, and so we have 4 over 5 minus 8 over 5, and we can write negative 2 as negative 10 over 5. So 4 minus 8 is negative 4. Minus 10, we get negative 14 over 5. And so the vertex is negative 2 over 5, negative 14 over 5. You could do this as a decimal, that's fine. I don't know what the 14 over 5 would be, but decimals are okay. I guess it would be negative 0.4 negative 2.8. I think that looks right. 14 divided by 5. Yeah, negative 2.8 and negative 0.4. This is also fine to do. Okay, a train station has 423 people at 9 a.m. The function here is denoting the number of people t hours after 9 a.m. So this tells us immediately that the initial value is 423. Initial value. So if it decreases at a rate of 3.2%, then R is negative 3.2%. Not K, because this is the normal growth rate, so it's R, and it's negative because it's decreasing. Writing this as a decimal would be 0.032. And then we need to use the fact that the growth factor is 1 plus R, which is 1 plus that number, which is 0.968. So then the function here is the initial value, which is 423 times 0.968 to the tth power. And that would be it. And we should check to make sure that this makes sense, but it does because this is less than 1. It's a growth factor less than 1, and the function should be decreasing. So that should line up. And as we said before, this has to be positive. So if it was negative here, that would be incorrect immediately. Increases at a rate of 6%. So this is similar, except now that R is positive 6%. B is 1 plus R, which is 1.06. And so then the function, same initial value, 423, 1.06 t. And then decreases at a continuous rate. So this is important. This says that K, and it's decreasing, so it's negative 1.63%, or negative 0.0163. And the initial value is still 423, and so the function now has to be in base E, negative 0.0163 t. You have to do this first. It is not necessary that you then, so you do not need to convert here for this problem, because it doesn't say so, to something like a times b to the power of t. You don't need to make the base b. This is a fine answer to provide. But also remember that you don't add or subtract 1 to k. It just goes directly into the formula for the function, and then you're done. Okay. So this account, this investment account, you start with $750. It doubles every 40 years, and we want to know a formula for the balance, and then also determine the yearly percent growth rate. So this is A, 750, and doubling the deposit means that the doubling time is 40 years. So then the function is 750 times base 2 power t divided by capital T, which is 40. And that would be it. This is the formula for the function. So if we want to know the yearly percent growth rate, we need to find the base or the growth factor for this function, which is 2 to the power of 1 over 40, because t over 40 is really 1 over 40 times t, just being explicit about the multiplication here. And then this means that we can split the power into t to the 140 power t. And then this is the base inside the parentheses. So that's b. And this is, if you compute it, something on your calculator to do, 1.0175. And then the growth rate is b minus 1, which would be 0.0175. And this is 1.75% would be the growth rate. And this should be positive because you're doubling. They're not taking money out of your account. And so the interest or whatever that you earn on this account, the growth rate should be greater than 0. And it is. Okay, write the function that, write this in the form a times b to the t. So in order to split this up, we need to recognize that 6 to the power of t minus 1 is, well, we're subtracting in the exponent, so it's sort of like we could have divided that this way, because if I start with this, then I would simplify it by doing 6 to the power of t minus 1, which is back to what I started with. So that's fine. And then we would write g of t as 570 times that, 6 to the t over 6 to the first power. The 6 can get absorbed into the initial value. And then this would be 570 over 6 times 6 to the power t, just being very clear about where the 6 is going. And this is 90. So actually, the base is the same as what we started with, but the initial value is different. So be careful about that. Okay. For this function, find the vertex, the horizontal intercepts, and then write it in standard form. And maybe this is a clue that you should try to do these two things first, and you should. The vertex is very easy to get. It's already in vertex form, so we already know that 7, negative 9 is the vertex. There's not really a lot of work that we had to do to get that. If we want to find the horizontal intercepts, we have to solve f of x equals 0. So that means x minus 7 squared minus 9 has to be equal to 0. We can add 9 to both sides. And now we have a positive number here and a square on the left. And so we can take the square root safely of both sides. that cancels out the square in that power, and so what I have left is x minus 7 equals plus or minus, I need both values here, the square root of 9, which is plus or minus 3, because the square root of 9 is 3. And I can add 7 to both sides, so I would have 7 plus or minus 3, which is true, but I could write this as, well, 7 plus 3 is 10, and 7 minus 3 is 4. And so the two horizontal intercepts are at 10, 0, and at 4, 0 as ordered pairs. If these involve radicals, you could leave them as radicals, but here we just know that the square root of 9 is 3. So if we want to put it into standard form, we then have to just expand out the product here. So this is x minus 7 times x minus 7 minus 9. Remember that if I square this, it's not x squared minus 7 squared. That's no good. And if I do this, I FOIL it or distribute it or whatever you want to call it, minus 14x plus 49, right? X, negative 7x, negative 7x, positive 49, minus 9. And so this is x squared minus 14x plus 40 in standard form. Okay. Solve this equation using the quadratic formula. First of all, it's not in standard form, so we need to write it in standard form. It's not in standard form because it's not set to 0. We need to move the 4 to the left side. So 2x squared minus 3x minus 4 equals 0. Now it's in standard form, so I can apply the quadratic formula. Here a is 2, b is negative 3, and c is negative 4. So the quadratic formula tells us that this is negative b plus or minus square root b squared minus 4ac all over 2a. Negative b is negative 3, which will just become positive 3. B squared is negative 3 squared, minus 4 times a, which is 2, times c, which is negative 4, all divided by 2 times 2 for 2a. So negative 3 is 3, and then I have 9 minus 4 times 2 times negative 4 over 4. And this is 3 plus or minus 9, and I'm doing, there's a couple of ways to look at this. If I look at just these terms, I have 4 times 2 times negative 4, and that is 32. So then I'm doing 9 minus 30, negative 32. Just rewrite that. Negative 32. So then this is 9 minus negative 32, because we still had the negative here. Which is 3 plus or minus, then I add that, and I get square root of 41 over 4, because these become plus. They cancel out, right? So that's what I get. A lot of students will make mistakes doing this computation here. Another way you could look at this is to include the negative 4 in as well. So then I have negative 4 times 2 times negative 4, which is 44. 32. So then I have the square root of 9 plus 32, as I absorbed the negative into the multiplication. Either way you want to do it, I guess is fine. Just be sure that you're not losing track of, you have a negative here and you have a negative here, and so you're really adding these numbers together, and your answer here should be positive 41. For the next problem, we have to find a formula for the exponential function here. There's a couple of ways to do this. One way is a little bit more simple, and I'll do that first, and then the other way is a little bit more work. The first thing that you could that you need to notice for either scenario you want to do is that this means that the initial value is 3. If you didn't notice that, you would then have to do basically the second approach that I'll take. So, but if you did notice that it's the initial value, then you know that A is 3. And the other thing you can notice here is that if you look at the outputs for the function, I have an output of 3 and I have an output of 6. So yes, I suppose that going from here in the outputs, I would have added 3, but that's not really useful. What is useful here is that 3 times 2 is 6, so I multiply by 2. So my output's doubled, so I know the doubling time. The doubling time is the distance, the horizontal distance here, I guess you should say, between these 2 points. It's the x value, or the time that it would take for the outputs to double, and that's from 0 to 4, because the x coordinate here is at 4. And so A is 3, and the doubling time, I should write that out, the doubling time is 4. And so then the function is 3 times 2 t over capital T here, which is 4. And so that would be the first approach you could make. It's a little bit more simple, it's a little bit easier if you had spotted it, but if you didn't, it's okay. You don't have to do it that way. You could have said, well, I know the initial value is 3, and I know that the other point 4 comma 6 is on the line, or on the function, so that has to be satisfied. So I can plug it in to the function here, where I don't know what the growth factor, the base, is. If I divide by 3, I get 2 equals b to the 4th, and so b is the 4th root of 2. We only want the positive one here, and this is about 1.1892. So then the function is a, which is 3, 1.1892 to the power t. And these should be the same function in the 2 approaches I took, and they are, because the base, as we saw in a previous problem, if I have a function that was like this, the base was 2 to the 1/4, which is the 4th root of 2 by definition. So, and that's this. So yes, these functions are the same. You could have left it in either form depending on what you did. Right, your base wouldn't, either one of these as written are fine to give as an answer. Okay. Here, P of t denotes the number of insets after an experiment begins. There's initially 300, so A is 300, it's the initial value. The population increases at a continuous daily percent growth rate of 5%. All of these are really important. So we know that K is positive 5%, or 0.05. And A is 300, that's the initial value, and so the function is A, which is 300, e to the power of 0.05 t. And remember that when we're given the continuous percent growth rate or continuous decay rate, whatever number you get as a decimal goes directly into the formula. We wouldn't add 1 or subtract 1 from it, it just goes directly in. That's not true for R, for the normal growth rate, but it is true here. How many insets are present after 20 days? So if I put in 20 for the function, then, right, because this is saying t equals 20, what do I get? Well, 300e 0.05 times 20, which is 300, and the exponential term is about 2.7183, and so this is approximately 816 if I round up in sets. present. And then convert this to the form of a times b to the t. So what we need to use here is the conversion that b is e to the k. You just split up the exponent, and this is e 0.05, which is 1.0513. And if I round to 4 decimal places, so then the same function can be written as 300 1.0513 to the t. And actually what this tells us, it tells us a bit more. It also tells us that the growth rate is b minus 1, which is 0.0513 or 5.13%. And that's very close to the continuous growth rate, which is 5%. And so it's not a coincidence that these are close. They're not equal here, clearly, but they should be close. If you do this calculation and they're not, you may have made a mistake somewhere in the conversion. For example, if you didn't convert this into a decimal first, it would be quite a bit off, and that should be a red flag. Okay, if these are power functions, write them in the standard form. So again, these should be negative coefficients. That's fine. So for the first one, this is the 7th root of 5 times the 7th root of x to the 6th. That's maybe the only way you could have gotten here, but it will work. It's using the property that if I do an nth root, any root of a times b, it's the same as the nth root of a times the nth root of b. And so this is the 7th root of 5 times x to the power of 6 over 7. We had to convert it into a fractional exponent because we wanted the power p. So then this means that k is the 7th root of 5. You could convert that to a decimal, I guess, if you want. And p is 6 over 7. Another way you could have gotten here is to say that this is 5. You could have converted it to a fractional exponent immediately. 5x to the 6th to the power of 1/7, and then you would get 5 to the 1/7 distributed in the exponents, which is the same thing. So either way you want to take it if you want to use this formula, or just convert it initially. Either way you'll get the same values. Here we need to distribute the -2 power onto the x cubed. You cannot just start working with these powers directly because the parentheses are indicating you're exponentiating, which is before multiplication division. So we need to do 8 times x. I'll just do it here. We're raising to the power, and so 3 times -2 is -6, 10x squared. And now we've gotten rid of all the parentheses. We can just subtract the exponents. We're dividing at the common base. 8 over 10 simplifies to 4/5, and this is then -6 minus 2, which is -8. And so this is 4 over 5, or 0.8, x to the -8. And this would be your standard form for that. And then for the next one, we can recognize that this is 3 times x to the 4th. The square root is the 1/2 power divided by 5x to the 8th. So 3, I raise to a power here, so I multiply 4 times 1/2, and I get x squared over 5x to the 8th, which is 3 over 5 x to the 2 minus 8, which is 3 over 5 x to the -6. And that would be my power function in the standard form. Okay, next there are 2 tables. Well, that's the other question. Are these functions described numerically? Are they exponential or not? So how can we tell? Well, we need to test if the inputs are evenly spaced. So first, to go from 2 to 4, we add 2, 4 to 6, we add 2, and 6 to 8, we add 2. And so we have evenly spaced inputs, which if you remember is the first condition you need to meet. The other condition is that when you multiply, there's a common ratio between consecutive outputs. So to figure out what this is, it's probably not obvious what I would need to multiply 3 by to go to 0.75. So how do I determine what these numbers are? I can divide them. So 0.75 divided by 3 is 0.25. And so I need to multiply 3 by 0.25, or equivalently divide by 4, but we want multiplication here to go to that number. And then I can do this again. What number do I have to multiply 0.75 by to go to the next? So I would divide them. 0.1875 divided by 0.75, and I also get 0.25. And so this number is also that, and then it's the same number here as well. You can check that works. So therefore, it is exponential because I have a common ratio, right, multiplication factor between consecutive outputs. And so it is an exponential function. What is its formula? So that's the next part of this, now that we determined that it is exponential. There's two ways to do this. So I'll show you both. The first option is that we might be able to adjust the table backwards. Because if I want 0, I want x equals 0. If I had that, this is the initial value a, and that's quite easy if it's in the table, but here it's not. So I can see that if I go backwards, I can do that by subtracting 2, right? And that still fits the table. The inputs here, that should be 0. I'm still adding 2 to go left to right, 0, 2, 4, 6, 8. So that is still in check. And if I want to go backwards with the outputs, well, if I'm going left to right, if I multiply by 0.25 to go the other way, I would multiply by the reciprocal of that, or 1 over 0.25, and that's 4. And so going from here to here, I would multiply by 4, 1 over this number, and 3 times 4 is 12. So this tells me that the initial value should be 12. And we can check that this works, because if I then pretend I started with this table now, and I went from here to here, I would multiply by, well, 12 divided by 3 is, or 3 divided by 12 is 0.25. And so that still works. So if you can hit 0 by moving backwards by the input spacing, and only by the input spacing, which here is 2, then I can determine what the initial value is. So by using that approach, a is 12. Now that I have a, life is a little bit easier, because now I know that the function is a times b to the x, but then a is 12, so it's 12b to the x, and I can put in a point and solve for a. So if I put in 3, 3 times 12 times b squared, then I divide by 12, and I get 3 over 12 equals b squared, and that's 1/4, so 1/4 equals b squared, and so b is the square root of 1/4, which is 1/2. So then the function is a, which is 12, times b, the growth factor, which is 0.5, or 1 over 2 to the power x. And so this is the formula for the function. You need to notice that this value is not 0.25. Just because I multiply here by 0.25 does not mean that b is that number. It's related, but it will not be the same value in general. So this is the first approach you could have taken. If you didn't notice that you could have moved the table backwards, what's the other approach you could have done? You could have just picked 2 points and then divided them. And so I'll show you that. So the second option is to just consider 2 points. So 2, 3, 2, 3, and say, it doesn't matter, they just have to be 2 distinct points, like that. And then I can plug them in, wait a minute, 4.75, yeah. So then I can plug them into the formula, and I would have 3 equals a times b squared, and I would have 0.75, the y value, equals a times b to the x value, which is 4. And then I want to divide these. If I put the bigger power on top, it's a bit easier. 0.75 over 3 equals a times b to the 4th over a times b squared. The a cancels out. It's a non-zero number being multiplied there. That goes away. On the left, I have 0.25, and then I have that equals b squared. And so b is the square root of 0.25, which is exactly what we saw before, which is good, which is 0.5. So that's the value for b. And then I need the value for a. So then I know now that my formula is a times b, which is 0.5 to the x. I can plug in another point. It can be the same one, it doesn't matter. So if I do, say, 2, 3, these numbers would go in here. This is 0.5 squared, and so a is 3 divided by 0.5 squared, which is 3 over 1/4, which is 3 times 4, which is 12. And so I still get the same function as I should here, but this is a way you could do it if you didn't see or you aren't comfortable or whatever reason, you didn't want to extend the table backwards. But also, again, you can only do this because I can only move by the input spacing. So as a word of caution, that approach, that shortcut that I did for the first question, for the first solution there, does not always work. And it does not work here because my input spacing is 2, as it was before. So I do have evenly spaced input, which is good. That's the first check. But if I go backwards, I don't hit 0. I have to subtract 2 and I hit -1. And I don't know what this is. And it cannot be determined. So yes, I guess 0 is in here somewhere. But again, we don't know what it is. Once I determine what the ratio between the outputs is, if I go backwards by 2, I can figure out what goes here. But that's not A. That's not the initial value. It's not the y-intercept. And so that approach will actually not work for this problem. So the table cannot be extended to the left to find A. It won't work. So we have to do another approach. First, we should probably finish checking that as exponential. So what is the number that I multiply here by to go from the nets? This is not obvious what this is. So I would divide them. The input on the right divided by the input on the left, or the output on the left rather. And I get 0.64. So I multiply here by 0.64. 0.64. And I can look at the next one. So 65536 divided by 1.024. That also gives me 0.64. So I also put that here. And the other one works as well. This is also times 0.64. So these are the same ratio. So the function is exponential. if one of these was different, say this was like 0.6, right? A little bit different than 0.64 or whatever, then it would be not. But here they're all the same, right? So it is exponential. And so we can find its formula, but we cannot use the shortcut that we saw before. So in order to do this, we don't have the initial value. We have to do the thing where we plug in 2 points. We can just pick the first two, but you can choose whichever ones you want. And then plug them in and then divide them. So the first one tells me I have this. The second one tells me I have this. And if I put the one with the bigger power on the top, I avoid negative exponents. It's just a little bit easier. So divide by 1.6, a b cubed, a b to the first power, a and a cancels. On the left, I end up with 0.64 equals b squared, because I have 3 minus 1, and I get the square. And then I can do the square root of both sides, because I have, right, b squared, do the square root, that cancels. So I have the square root of 0.64 equals b, and then so b is equal to that number, which is 0.8, if I do the square root in the calculator. So now I need the initial value. So now I know that the function, I can update it with what I just found, is a times that number 0.8 to the x. If I plug in the point, say 1.6, I get a 0.8 to the first power. So here I plugged in, you could use any point, but I did 1.6, and so then a is 1.6 divided by 0.8, which is 2. And so the function is 2 times 1 b, which is 0.8, to the x. And that's what I end up with. So in a sense, maybe we could see that if I went back here by 2, just to show you that this won't work, I hit -1. And if I go the other way, I'll get the output here, which I don't know what it is. And then 0 is at 2. And 2 times 0.64, sorry, nope, nope. So I don't know what number multiplies here. That cannot be determined using this value, because this is using an input spacing of 0.2. And if you change the input spacing, the output ratios will change. And so just be careful that you only use this approach if you know that you'll hit the intercept as you would for that example up there.